So now, instead of some inert solvent, I'm going to name my solvent. I'm going to use water. But maybe a bigger change is that instead of using excess HCl, so way more than I need, I'm actually going to add catalytic HCl. So what do I mean when I say catalytic? Well, first and foremost, a catalyst is not consumed in a reaction. It's not used up. So that means that in theory, I really could get away with only using one molecule of HCl, right? So just get to the bottom, HCl, my catalyst lowers my activation energy. So it's meant to increase my rate. But because it's not consumed, I can think about it sort of this catalyst molecule just making one reaction go at a time, right? So that would take forever, so I'm going to add more than one molecule of catalyst. But the idea is that I don't need a full equivalent. I should need quite a bit less. And so my catalyst is not going to be incorporated into my product, which is to say, I'm not going to see a product with a chlorine in it because I probably don't have enough to go around. I probably don't have enough chlorine atoms for all of these molecules. Okay? So that's what I mean by catalyst. A catalyst lowers the activation energy for the reaction to increase the rate. The catalysts are not consumed in the reaction. They're not used up. And so my product will not have a catalyst in it. Well, then what will it have? Well, let's go through it. So just like before, my intermediate is going to be this tertiary carbocation. Now, what can that react with? Well, it can react with some Cl-, but frankly, there's not a whole lot of that to go around. And what I left off talking about here is that this is a reversible reaction. That carbon-chlorine bond isn't that strong. And so even if the chlorine does add, it can pop back off, back and forth. You know what there's a lot of in this reaction? There is a lot of water. Frankly, there's probably not even any HCl. It's really HO. There's a lot of water. If I'm being honest, there's probably no HCl. Because remember, HCl dissociates in water. So I don't actually have HCl. I have H3O+. But H3O+ will do the same thing that HCl is. It will react with that. It'll react with that alkene to give me this intermediate. So I have this intermediate. I have water here. Water has lone pairs, excess electrons. So water is actually going to act as my nucleophile and make a new bond here. So here, notice all I've done between there and there is make a new bond between oxygen and carbon. So now here, this carbon has the positive charge. Here, this oxygen carries the negative charge. So we didn't destroy any charges in that reaction. This is really important. Notice that water is a good enough nucleophile to react with this really, really reactive thing. So usually water isn't super reactive, but this is super reactive, and this is reactive enough to react with anything. Notice that I didn't have to break an OH bond to attack this. Water doesn't really spontaneously give me that much H3O+ and OH-. You think back to general chemistry, this constant is something like 10 to the negative 14, real small number, all right? So please, please, please don't say, oh yeah, water just breaks a bond and then this goes and attack, all right? It doesn't need to and it doesn't happen. So water attacks this carbocation, I get this intermediate. So this is a pretty strong acid, right? Oxygen doesn't like to have a positive charge. And so what can this do? Well, this is a strong acid. It'll protonate anything around it. And so what's around it? Well, like I said, there's a lot of water around. So water will now take this extra proton. This is just an acid-base reaction, reversible, all this is. And so what I end up with is an alcohol. I have an alcohol product, and I end up with H3O+. That is my catalyst. It re-enters the catalytic cycle. Okay? So that's what I mean by I really only need one molecule of catalyst, right? Because I use it at the beginning, and it gets generated out at the end. So it takes it in and spits it out at the end. Now we know two different reactions. We can start with an alkene and get an alkyl halide by treating it with excess acid, HCl, HBr, etc. Or we can use a catalytic amount of strong acid in water and end up with an alcohol. This is called a hydration reaction. So we're starting to build some power, right? We're able to make a diverse amount of things. One thing I want to point out is that both of these things are equilibrium, and that it's not as clean as I make it say, right? So if there's some water in here, you'll get a little bit of alcohol here. Here, you can reversibly form some of the alkyl halide here. So you should think about all of this as an equilibrium mixture that I can push one way or the other using Le Chatelier's principle, right? So if I think about all this as one big system, and I say, gosh, I really want this alkyl chloride at the end, then I'm going to just push more HCl on it, right? Because HCl will push it to this side. If I say, no, I think I want the alcohol, well, then I'm going to give it some water. I'm going to make sure it has enough water to push it to the left side. So all of these things are under equilibrium and under our control. Yes. Let's do another example. So here I've got another alkene, and I'm going to put that alkene in methanol with some catalytic sulfuric acid this time. So remember, when I say catalytic acid, it means that it's not going to show up in the product, so my product better not have a sulfur atom in it. Simply, this is a really, really strong acid. I'm probably going to dissociate even in methanol like I would in water. So really, that's my acid. My alkene is going to go grab an acidic proton, just like it would have if I'd have reacted with HCl or HBr. Again, there's lots of solvent molecules around this thing. So as soon as I form that positive charge, my methanol is going to act like a nucleophile and go after it. Do I need to break this OH bond first before I do that? Please don't, right? In strong acid, the last thing that's happening is for me to make strong base, right? So if I've got strong acid in the pot, there's no way there's O- in there at all, okay? So don't mix strong acids and strong bases, even on a chalkboard or even on a whiteboard or whatever this is, much less in real life. So those electrons go after the carbocation. Notice, I didn't break any bonds, I just made one bond, and I didn't lose any charges. This is overall plus, this is overall plus. But now this, I can just simply look at as a strong acid. Again, right, this OH makes it a very strong acid. And there's enough methanol around for me to use methanol to grab that acid proton. Here are my products. I get an ether. So before, with water, I ended up with an alcohol. Now, with methanol, I end up making an ether. And I also end up with this strong acid that is now going to re-enter the catalytic cycle over there. Okay, so again, this is catalytic and acid. Acid turns the crank, but doesn't show up in the final product. Now I know how to make 3 different functional groups from an alkene. I can make alcohols, I can make alkyl halides, I can make ethers. The idea is that all of these are variations on a theme. And in particular, all of these share a common intermediate, right? They are all coming from this cation. And so if we think about this as coming from a common intermediate and just reacting with different nucleophiles. So here the nucleophile is just the chloride left over from the HCl. In these cases, the nucleophile is the solvent, right? But in all the cases, they all work the same. They're all coming from a common intermediate. And I can probably think of other solvents that I could use that would add to that cation in exactly the same way. So I know it sounds like individual solvents, and you're tempted to latch onto these words and memorize cue card by cue card. That's not a terrible way to go, but I hope that you can take a step back and see what links all this together. What links all this together is a common intermediate and a common mechanism. They all fit together.